A very good morning and welcome to this 30th lecture in 303 heat transfer. We'll be talking about boiling and condensation heat transfer today. So till now in convection we've talked about the forced convection first, where the flow velocities are forced. Secondly, we talked about natural convection, and now we'll talk about phase change heat transfer, where the heat transfer coefficients are much larger than what we get for forced convection as well as natural or free convection. So in this discussion we'll talk about the convection rate of heat transfer associated with a change in phase. So the change in phase can be boiling. So boiling occurs typically at a solid liquid interface. So the solid would get heated up above the saturation temperature, and the liquid would then liquid contacting the solid would then start boiling, that is converting to vapor phase. We can also have condensation, where which happens typically at a solid vapor interface, where a solid which is below the boiling point condenses and results in the vapor condensing into a liquid on the surface of the solid. As we know that latent heat associated with phase change is quite large, and this means that we typically are talking about large rate of heat transfer for small delta t's. So we have to understand here what is the meaning of delta t, because phase change happens at the saturation temperature. So since for boiling and condensation the surfaces are either above the saturation temperature or below the saturation temperature, so Ts, which is the surface temperature, let us take boiling for discussion. So Ts is the solid surface temperature which is above the saturation temperature. So this delta T then becomes the difference between the solid surface temperature and the saturation temperature for the liquid that is going to boil. And the rate of heat transfer Q, this Q is then written as the heat transfer coefficient H, which is again this is some sort of a definition for this heat transfer coefficient H for phase change heat transfer phenomena, that is boiling and condensation, with the delta T given as Ts minus T saturation. And of course area is the area of contact between the two surfaces, between the solid and the liquid, in this case a solid and the vapor. And this rate of heat transfer can also be written as the mass flow rate m dot times the latent heat H fluid gas. Okay, so this is how we define our H. So what we can do is we can calculate H using this relation. Okay, so in boiling heat transfer happens from a solid surface, whereas in condensation the heat transfer happens to a solid surface from the vapor. Now where is convection coming into the picture in this situation? The fluid flow in this case results from the boiling and condensation phenomena. So for example, in boiling, when a vapor bubble is formed at the surface of the solid, which is the hot solid surface, so this vapor bubble will tend to rise because of buoyancy. Okay, and as the vapor bubble rises, it creates a convection current in the whole system, or the cell where the convection is happening, where the boiling is happening, and this results in fluid flow resulting from this bubble rising, and these convection currents then result in increased heat transfer coefficients. So in boiling and condensation we see a combined effect of buoyancy. So in this case, as I said, that as the bubble rises it creates a convection current, latent heat. So the amount of heat extracted by the bubble is large, because latent heat typically is very large. We also see rather than just the flow above the solid resulting from the bubble moving, because the fluid, let us say the bubbles have still not formed yet, the fluid above the solid surface is also getting heated, and we are also getting some natural convection currents because of the hot liquid above the solid surface. So the combined effect of all these effects, the combined effect of all these phenomena result in an increased rate of heat transfer from the surface. So these are a few applications of boiling and condensation. So we see a boiler in here. So this boilers like this are used for converting liquid to gas. You would see them a lot in the minerals processing industry as well as the energy industry. High pressure liquid is converted to gas in this cycle. You also see them in where you have turbines because you want to produce steam for running turbines. The other is condensers, as here. So you see a condenser where the steam is hot steam is condensed into a liquid, or any hot vapor or any vapor is converted to a liquid, and these again are typically seen in power plants as well as in your vapor refrigeration cycle. The other applications are um, thermal management of electronics, for example uh, sorry heat pipes like this, as you see here in the computers, etc., where instead of just transferring heat which results in a sensible heating, that is increase in temperature of the liquid, uh, we there's a phase change that happens. So the liquid which is contacting the hot surface will result in a phase change, so it will extract a large amount of heat because it will change its phase into a vapor, and this vapor then again will be condensed later, and that will result in this vapor giving a large amount of energy to some cold surface, and again convert to liquid, and this process will continue in these heat pipes, resulting in a large amount of heat transfer and allowing thermal management of electronic components which can get really hot because of the high power they deliver these days. So we will start our discussion with boiling first and then move on to condensation in the second part of this lecture. In boiling, we have typically 5 non-dimensional parameters that are important. Actually, these non-dimensional parameters are important in both boiling and condensation. So the Nusselt number, of course, which we are interested in finding, because we ultimately have to calculate the heat transfer coefficient, and then the Q, the watts, the rate of heat transfer. So the Nusselt number depends on these 4 non-dimensional parameters. The first one here being something which looks like a Grashof number. If you recall the Grashof number from the natural or the free convection discussion in the previous lecture, so here the only difference is that instead of the density difference that we had written as rho minus rho infinity, we have the rho liquid minus rho vapor. We're talking about phase change here, so that's the reason we have rho liquid and rho vapor here. And then we have something called a Jacob number, which is given as the Cp, that is specific heat, times delta T. Now, delta T here is the T surface minus T saturation, and in the denominator we have this latent heat. Then we have the Prandtl number as earlier, and then we also have something called a bond number, which includes the effect of the difference in the density and the gravity as well as the surface tension. Okay, so let's visit these parameters again in a bit more detail. So the Grashof number, or the number that looks like a Grashof number here, is is um, is bringing in the effect of viscosity as well as the density difference. Remember that it is the difference in the densities which results in the fluid becoming buoyant. So bubbles, for example, when they are formed in boiling over a plate, they start to rise up. And so this is a ratio of this force of buoyancy as well as to the viscosity. Okay, so if the viscosity is high, then they have lots of resistance. If the viscosity is low, then they can move very quickly. Then the Jacob number, which has the effect of the supersaturated temperature, or the temperature of the solid above the saturation temperature of the liquid. So this the numerator has the effect of sensible heating. So that is the temperature increase, the maximum temperature increase that can occur, because you can't heat a liquid. The solid plate temperature is T surface, so you can't have temperature more than T surface in the fluid. And the denominator has the effect of latent heat, which of course is non-sensible, so it occurs at the saturation temperature. So Jacob number typically is because the amount, the contribution of the latent heat is significant. So this number is typically small. Then you have the bond number, which brings in the ratio of the gravitational effects, the surface tension effects. So when you're dealing with tiny drops which are condensed on a surface, then the surface tension is force becomes significant. That is the reason you see these tiny spherical beads. But as the drops become larger and larger, they tend to settle down because of the effects of gravity. So the bond number is also important because you're dealing with boiling or condensation happening over surfaces where the surface tension effects, the interfacial tension effects, start to dominate. So let's talk about the Newton's law of cooling for boiling. So as earlier, Newton's law of cooling helps us calculate the heat flux here, and this is written as the heat transfer coefficient H, which of course this law defines, times the delta T, the excess temperature as we call it. So this is the difference between the saturation temperature of the liquid in boiling and the excess temperature of the solid surface, and we'll talk about it later. So this, as we discussed earlier, that the bubbles form on the surface when the solid surface becomes very hot. The bubbles grow, and as they become larger because of the buoyancy force, they rise up in the liquid as they're lighter, and in the process of rising up they detach from the surface, and these bubbles then uh, apply a force on the liquid which is equal and opposite to the drag force the liquid applies on the bubbles. So this creates currents in the liquid in which the bubbles are rising. You may have seen that when you're boiling water, so the whole water starts to mix vigorously, and this large amount of mixing in the fluid is responsible for high heat transfer coefficient, because one, the bubbles are taking away a lot of heat from the solid, and the whole idea of convection is that the heat transfers from the solid into the liquid. So these bubbles in the process of forming, they take a large amount of heat because of latent heat. So that is one, and then as they rise up, they take this heat away, or this energy away from the surface, and the energy gets released on the surface as vapor. So this combined process of latent heat extraction, mixing of the fluid, as well as the buoyancy, this results in a large amount of heat transfer, which is quite desirable when we want to lose heat as quickly as possible. So here are a couple of special cases which we use to characterize types of boiling. So the first class is pool boiling and forced convection boiling. So in pool boiling, the liquid is, is an quiescent state. That is, when you're boiling water in a pan, then the whole liquid is stationary, and the only motion that develops in the liquid is because of natural convection of the bubbles moving in the liquid. So this is bubble induced mixing. Whereas on the other hand, we have something called a forced convection boiling, where the motion of the fluid is forced. So you may have an external means which is used to move the fluid in addition to the bubble induced mixing that is caused. So this is forced convection boiling, which results in higher rate of heat transfer because you're also assisting the liquid to move as quickly as possible away from the surface, and the bubbles are also removed away quickly from the surface. The second way we characterize boiling is saturated versus subcooled. So in saturated, when a bubble when a bubble forms, that is when the liquid converts to vapor, most of the other liquid around that bubble is at a temperature which is slightly larger than the saturation temperature. So if at the atmospheric pressure, the saturation temperature is 100 degrees centigrade for water, so most of the liquid around the bubble will be slightly more than 100 degrees centigrade. Whereas in subcooled boiling, most of the liquid is slightly less than the saturated temperature. So what happens is when the bubble rises, since most of the liquid around it is below 100 degrees centigrade, it cools and then it condenses by the time it reaches the top. So this bubble is not able to get released from the top surface. Of course, saturated boiling is preferred when you want high rate of heat transfer, or high heat transfer coefficient. Okay, so we'll summarize what we have discussed quickly again. So boiling is associated with transformation of liquid to vapor. Okay, and this agitation in the fluid that we see results in large convection coefficients, and hence you have large heat fluxes. And remember that all this is happening at low to moderate surface to fluid temperature differences, and that is really good because you don't want to spend lots of energy to heat the solid surface to a very high temperature. So even though you are at only 105 degrees centigrade, let us say, for the solid surface, but that results in a large amount of heat transfer away from the solid, which may be preferred in many situations where you want to cool the solid, or allow large amount of heat flux to leave from the solid. And we already have discussed this special form of Newton's law of cooling, which uses the excess temperature, which is the temperature of the solid above the saturation temperature of the liquid. So next we will talk about the boiling curve, because we in the Newton's law of cooling, if you would want to understand how the heat flux from the solid surface is related to the excess temperature, because remember, Newton's law of cooling is just a law. You can't obtain it from first principles. So this Newton's law of cooling helps us define our heat transfer coefficient. So for that we have to understand the behavior of the heat flux as a function of the excess temperature in real situations. So this is the curve that we have for the heat flux versus excess temperature for water at atmospheric pressure, and this experiment was conducted by Nukiyama, where he used a nichrome wire, okay, which was later converted to a platinum wire, but the experiment was conducted first time using a nichrome wire. So let's discuss this. So this is saturated pool boiling, that is most of the liquid around, most of the water here is at a temperature was at a temperature which was slightly above the saturation temperature. And here what he had was, he had a wire. So it was simply a wire made up of nichrome, which and he allowed the current to flow through the wire, so that resulted in the resistance heating of the wire, the I square R heating. And this wire was submerged in a vessel which was filled with liquid at 1 atmospheric pressure. Okay. So what happened was that as the temperature of the wire was increased by increasing the potential difference across the wire, because that resulted in increasing the current through the wire. So as the potential difference across the wire was increased, as the resistance or the heating, the Q double prime from the wire was increased, this resulted in the boiling to start on the surface as the temperature increased above the saturation temperature, and these bubbles started to rise. And this was analyzed by measuring the QS double prime, which was the amount of heat leaving as convection from the wire to the liquid, and this QS double prime actually was is equal to the the watts per meter square. So the watts is the electrical watts. Okay, so you can multiply your potential difference by the current through the wire. So all the energy that is getting released from the surface of the wire has to leave out as convection. Okay, we are neglecting radiation right now and as well as conduction. So most of the energy, almost all of the energy from the wire is leaving as convection into the liquid. So let us first analyze the curve. Let's try to understand it, and then we will give some theory to explain why this phenomena is observed. So firstly, when this excess temperature delta TE is increased from 1 to 5 degrees centigrade, that is when the surface temperature is less than 105 degrees centigrade, you see that your heat flux is quite minimal. Okay, so what and so this is what is shown here. As you see here, but as the temperature of the surface of the nichrome wire is increased further by passing, of course, more current. Well, actually in this case we are not controlling the experiment by controlling the excess temperature. We are controlling the experiment by controlling our Q double prime, because all we can control is the current or the potential difference across the wire. So as we increase the potential difference, our QS double prime increases. So as we increase this, we see a stark increase in the temperature, excess temperature or the surface temperature, as the heat flux increases, and then we reach a point where the heat flux Q double prime becomes a maximum. Okay. So remember, we are controlling using a potentiometer. We are controlling the voltage across the nichrome wire, and as we try to increase the QS double prime further by increasing the potential difference across the wire, we see that there is a sudden increase. As you see from this arrows, um, you jump from this point of the curve to this point. Okay, so that means that there is a sudden increase in the temperature of the surface. So the solid surface of the nichrome wire surface increases suddenly. Okay, so there's a stark increase from 30 degrees all the way to 1000 plus degrees. And then well, for the nichrome wire the melting temperature is here. So what happened was that as soon as we tried to increase the Q double prime by increasing the potential difference across the wire above this Q prime double prime max, this resulted in melting of the wire at this point. So there's nothing we could do beyond this point. Okay, so this situation was called the burnout of the nichrome wire. Now to analyze the curve further in this range, this nichrome wire was replaced with the platinum wire. So as the melting point for platinum is around 2500 Kelvin as opposed to 1500 Kelvin. So as the melting point for the platinum wire is 2500 Kelvin as opposed to 1500 Kelvin for nichrome. So the experiment was conducted again using platinum wire then, and then what was noticed was that since the, the platinum wire can go further up from here, because we still are much below the melting point for the platinum wire, we could trace this curve. And then what was done was that the potential difference across the platinum wire was started to reduce. So when we reduce the potential difference across the platinum wire, the the thing started to cool, the wire started to cool. And then while we measured the surface temperature of the platinum wire while reducing the potential difference across this wire versus the power loss or the heat loss from the wire, we traced this curve for US double prime versus delta D excess, and then there was a point called Q double prime min. That is a minimum value that we obtain, at least the local minimum here. And then beyond that, we as we try to reduce the potential drop across the platinum wire further, the curve shifted to this point. So this is the path curve took. So there was a sudden while trying to vary the Q S double prime continuously, the curve shifted from this point to this point. So there was a sudden decrease in the temperature of the platinum wire surface, and this then was traced back to the same curve. Okay, so this was we could not obtain using this Nukiyama's experiment. One could not obtain the this dashed part of the curve. So this when the experiment was later conducted by Drew and Miller, who were able to carefully control the surface temperature of the wire rather than the heat flux. What they used was they used steam flowing in a pipe to control the wire surface temperature, and the steam temperature could be controlled by changing the pressure. So as you know that the boiling point can be controlled by changing the atmospheric pressure. So the temperature could be controlled for the wire, and that resulted in this dashed part of the curve to be obtained. So then as the excess temperature was or the surface temperature of the platinum wire was controlled continuously, we saw that while increasing the surface temperature, this curve was obtained, and while decreasing, we could retrace this curve back. Okay. So it was a very useful experiment because this helped us calculate a relation between QS double prime and delta T. And remember, Newton's law of cooling, all it does is this only. So Newton's law of cooling says QS double prime is H times delta T excess. So we can simply divide for a given position, let's say on the curve, we can calculate the heat transfer coefficient by taking a ratio of QS double prime and delta T excess. Okay, an extremely important experiment for understanding the heat transfer coefficient in boiling. Okay, so let's analyze things further. So in a free when the delta D excess is between 0 and 5 degrees centigrade, in this region what happens is on around there's not much bubble formation. So what's happening is the wire is getting hot, and this is resulting in the liquid that is contacting the wire above the wire to get hot, and that liquid as it gets hot, it starts generating free convection currents. So if there's free convection happening, then you will see some sort of heat transfer from the surface. So that is what is called free convection boiling. Okay, the word free convection tells us that most of the liquid around the wire, most of the convection happening from the wire is because of free convection. Although we may see one or two bubbles getting formed, but mostly it is free convection. So liquid motion is primarily due to natural convection, single phase. So beyond this 5 degrees centigrade, what we see is that there's an onset of nucleate boiling. Okay, so lots of bubbles start to form. So the region between 0 and 5 degrees centigrade is free convection boiling. And remember, the water here is at 1 atmospheric pressure for this experiment that we have demonstrated. So beyond a delta T excess of 5 degrees centigrade, as I mentioned earlier, we have an onset of nucleate boiling. So what happens is lots of bubbles start to nucleate on the surface. This surface that you have, well, I should draw it here. So the surface that you have, bubbles start to nucleate beyond this point A, and when the bubbles nucleate, they rise up because of the buoyancy, and this results in the fluid which starts to recirculate, because remember, these bubbles are buoyant, so as they rise up they push the liquid further, and this liquid above the bubble starts to rise up as well, but then that creates some sort of a vacuum, and then a low pressure, and that pulls in the fluid from around this region. So we see some sort of a recirculation in this vessel, which is heated from the flame below. This You see some sort of recirculation in the liquid. Okay, so as the cold liquid gets pulled in and the hot liquid rises up, because of these nucleus, bubble nuclei moving up, this results in an increased rate of heat transfer, and that is what you see between points A and B. Okay, but remember, these bubbles are isolated bubbles. We don't have lots of bubbles in this between point A and B, and the bubbles are not interacting with each other a lot. But beyond point B, we start to see beyond this point B, we start to see that bubbles start to escape as jets. So as you may have seen, when you try to boil water on a pan, beyond a point it becomes very loud. You see a lot of noise in the pan, which somehow it also looks like this figure. So on the surface you have these vigorous bubble formation that happens on the surface, and the bubbles leave as jets or columns, and they start merging into slugs, um, which results in a lot of turbulence on the surface and an increased rate of heat transfer from the surface. And that is what we see between points B and P, that there is an increased amount of heat transfer that we see. Okay, but this interference due to the bubble interaction and lots of vapor that gets formed on above the surface. So if in this figure for nucleate boiling, if I show it here, so just above the solid surface you see a lot of vapor bubbles have. So most of the surface is covered with vapor bubbles because of lots of nuclei of vapor. So what happens is there is some sort of resistance that starts because of the interference of bubble above the surface, as well as the coating of vapor that starts to form on the surface. The rate at which the heat was increasing starts to decrease. So between point P and point C, we see that this curve starts to flatten because of the resistance, because of bubble interference just above the surface, as well as the vapor covering the surface. And ultimately at point C, we see a maximum in the heat flux. Now remember, in this experiment all we are doing is we are controlling QS double prime by controlling the potential drop across the platinum wire. So when we try to increase the potential drop across the platinum wire, that is, we try to increase the QS double prime, beyond this point P the curve jumps. But as I said earlier, that in the experiment by Drew and Miller, they could calculate the excess temperature delta TE by controlling the surface temperature of the platinum wire. So what happens is, beyond this point C, where we have the maximum surface the flux, as we increase the excess temperature further, uh, what we see is that the transition boiling regime starts. So between point C and D we have a transition boiling regime. So there is a transition between nucleate boiling, which is characterized by a rigorous mixing above the surface because of the bubble formation, and a film that forms on the surface. So this film that forms on the surface provides resistance to the flow of energy, flow of heat. So this film, as we know that the vapor has a conduction resistance which is much larger than the resistance to conduction for liquid. So this film blanket that starts to form on the surface with increased surface temperature results in a decrease in surface heat flux. So that's the reason the curve starts to drop. And we reach a point D where the surface heat flux is minimum, um, and uh, beyond point D, what happens is, although the vapor still is there and it is still resisting the convection heat flow, but radiation starts to dominate. So this D is that optimum point where beyond which the rate of energy that is leaving the solid surface due to radiation starts to dominate, and as we increase the excess temperature further from here beyond 120 degrees centigrade, the radiative loss from the surface results in a consistent increase in the QS double prime. Okay. So let us now try to calculate the heat transfer coefficient, because as we said that the Newton's law of cooling in this case is simply QS double prime is modeled as a heat transfer coefficient times the excess temperature. So if I look at a point, let's say where my QS double prime was maximum, which was this point C. So for this, my QS double prime is approximately slightly above 10 to the power of 6. So if I'm trying to calculate my H at point C, so this is 10 to the power of 6 approximately, divided by the excess temperature here is 30 degrees centigrade. Okay. So this results in a value which is which is approximately 3 times 10 to the power of 4 watts per meter square Kelvin. Okay. So if you compare this 30,000 with a meager 7 or 8 or 10 watts per meter square Kelvin that we got for natural convection, and around 200 or 300 that we used to get for forced convection, this is extremely high. So what we see is that we can actually obtain very large heat transfer rates using this mode of boiling. Okay. So this idea typically is actually used for applications which require a large amount of cooling, surface cooling. So for example, nuclear reactors. So these nuclear rods become very hot. To increase the rate at which you lose energy from these nuclear rods, we use boiling heat transfer. So this is phase change phenomena associated with it results in very large heat transfer coefficients, which can then use for cooling the system as quickly as possible. So you can run the system at a very large performance, uh, because you don't want the rods to melt. Because if you're not able to release the energy from the rods using convection in this case as quickly as possible, then the rod temperature will start to increase a lot, and that will result in the melting of the rods, and melting of nuclear fuel rods in a nuclear power plant is not a very desirable situation. But at what point should we run this boiling? Because the excess temperature, we have to tune the system so that we have the maximum rate of heat loss. So if you see this graph, then what we can see is that we are obtaining, well, in this curve, there is one point here, which is point number C, where we have a large value of heat transfer coefficient, or we can also go further beyond this point where we have a large value of heat transfer coefficient. But beyond point E, you are working with very large excess temperatures, which again is not desirable, because a very large value of excess temperature, that is a large value of the surface temperature of the rod, can result in melting. So point number C is the optimum point that you have, where the excess temperature is quite small. Well, this is water we are talking about, so it's 30 degrees centigrade. So if you are cooling nuclear rods using water, which is typically what is done, so you're dealing with a surface temperature of only 130 degrees centigrade, which is really good, and your heat loss is extremely high, which is also very good. Um, and this point C is called the critical heat flux point. Um, but the scary thing about running at point C is because if you slightly increase the heat flux, you suddenly jump to point E from C, and this point E is extremely high surface temperatures, which can result in the melting of the nuclear rods. So although it is C is the optimum point, but because it is very close to E, so we tend to run the system slightly below C, somewhere here, so that we have enough control range available to prevent the jump from point C to E. And then we can also run on a very high value of heat transfer coefficient in this region. Okay, so we do not want to exceed the critical heat flux value. And there's another point which I did not mention. This point D is called the Leidenfrost point. Okay. So this idea was given by Leidenfrost, that beyond point D, it's the radiation rate of heat transfer that starts dominating. Just as terminology. So a quick summary of what we have discussed till now. I'll run through it very quickly. So nucleate boiling was between 5 and 30 degrees centigrade of excess temperature, where the isolated bubbles form between point A and B, where delta T excess was between 5 and 10 degrees centigrade. This is what was happening here. Um, but beyond that, you had jets and columns. So that was when the delta T excess was between 10 and 30 degrees centigrade, where you had this vigorous mixing happening in the liquid. So increased nucleation, formation of jets and slugs of bubbles. There's an impaired surface contact between liquid and surface. Most of the surface is covered with vapor here, and QS prime double prime continues to increase, but the rate of this starts to decrease. So H starts to decrease, because the rate at which Q increases is much less than the rate at which delta T increases. So then we have a critical heat flux point, which is the point at which my delta QS double prime is a maximum for water at 1 atmospheric pressure. It is around 30 degrees centigrade. So you obtain the maximum heat flux for nucleate boiling range, which is around half a megawatt or 1 megawatts per meter square. And but beyond this point, we can have a potential burnout, because there is a sudden increase in the excess temperature as you go beyond Q double prime max, that is a critical heat flux point. Uh, and this is because since as we saw beyond the transition range, there is a blanket of vapor above the surface. So that blanket of vapor decreases the rate at which energy is lost, and that results in an increase in the surface temperature. And we have a film boiling situation where the surface is covered with vapor. So this film boiling situation has a vapor blanket. So as you can see from this figure, you have a vapor blanket here, and Leidenfrost point is obtained, beyond which the radiation mode of heat transfer starts to dominate. Okay, so I will quickly run through this. All right, so correlations. So remember, although we showed you a figure, but that figure is not available all the time, and you would typically want some sort of a correlation that can be used to calculate, substitute variable values and get numbers for Nusselt number. Okay, so one correlation is given here for your surface heat flux in terms of your excess temperature, delta T excess. Okay, so you need all these parameters as we discussed in the beginning about those Prandtl number, Jacob number, Bond number, as well as the modified Grashof number. So we can put these variable values and get our heat flux which typically is what we want to calculate as a function of our excess temperature. And you can calculate your heat transfer coefficient as well from here. Okay, then as I said that you would want to operate in a critical heat flux region around just behind that, because the heat transfer coefficient associated with critical heat flux is maximum. So you can also calculate your critical heat flux value using this correlation that's given to you. Okay, for the film boiling regime, you would want to use a slightly different correlation, which is given here. Again, I won't go into lots of details of this, because that is not the idea. The idea was to explain the mechanism to you, and then these correlations can then be searched and you can use them whichever works best for that situation. Okay, so we have lots of correlations here as well, and in the exam, if required, I will give you the correlations and you'll have to choose the best one for that situation. So let us solve a problem. This is a problem from the book, which is problem number 10.23 from the textbook. So in this case, you have semiconductor cooling performed using boiling heat transfer that we have discussed. So you have a silicon chip that's given here, and the chip has a thickness of 2.5 millimeters. So this L is 2.5 millimeters, and the thermal conductivity of the chip is also given, which is 135 watts per meter Kelvin. And this chip is cooled using a saturated fluorocarbon liquid, which is this liquid above the chip given here, and this has a saturation temperature of 57 degree centigrade. Yes, like water has a saturation temperature of 100 degree centigrade, this fluorocarbon has a temperature of saturation temperature of 57 degree centigrade. Okay, the electronic circuits on the bottom of the chip. So the chip is pasted on some surface, and the electronic components just below the chip are generating heat with a uniform heat flux of Q naught double prime, which in this case is given as 5 into 10 to the 4, which is 50,000 watts per meter square. And we are assuming that the sides of the chip, which are these two sides on the left and right, are insulated perfectly. So the only heat being given to the chip is from the bottom, and the heat loss is occurring from the top, where you have the saturated fluorocarbon um, contacting the chip. So what we have to do is we have to find the steady state temperature of the bottom surface of the chip. So this is denoted by T naught. Okay, so that's the first part, and the second part is during testing on the chip, what typically is done is we try to run our semiconductor or the computer at a very large performance value, which is a very large heat being generated. So for testing of the chip, we have a Q naught double prime, which is equal to 90% of the critical heat flux. Remember, we don't want to go beyond the critical heat flux situation. That is not desirable. So the max operating condition that we have is 90% of the critical heat flux during testing. So we have to figure out what the bottom temperature is for that 90% of the critical heat flux situation. So basically we are given two different values of the Q naught double prime, and we have to calculate the bottom temperature of the silicon chip for those situations. Remember, bottom temperature is greater than the top temperature because of the conduction heat loss. Bottom temperature will decide the design criteria. So the silicon chip should not go beyond a certain temperature, otherwise it will deform, and it will fail, so to say, by not performing properly beyond that temperature. So let's solve this problem. Now this chip that we have, which is getting heat from the bottom. So from the bottom you are getting Q naught double prime, and that is conducted into the chip. So you have Q prime conduction, and that is then convected to the liquid through boiling. And this is the energy balance we have. So we can write this Q naught double prime equal to Q naught double prime conduction, and we know that the conduction in this case can be the conduction flux can be written as the potential difference, which is T naught at the bottom and Ts at the top, divided by the thermal resistance, which is L upon Ks. Okay, so that's one equation we have, and this is equal to Qs double prime, which is the convection. So I'll write it Qs double prime, because that is what we have been using for the energy loss from the surface. Okay, and this relation between Qs double prime and delta T excess is what we just saw in the correlations I showed you. So we'll use the Rosenau's correlation, which relates the excess temperature versus Qs double prime. So Qs double prime is known, which is equal to your Q naught double prime, which was given, and T saturation is also known. So from this correlation you can finally calculate the value of T surface. Okay, so once you have the T surface value, which in this case, well, the delta T excess is 15.9 degrees centigrade, so that gives us a T surface of 72.9 degree centigrade. So that's the temperature on the surface of the on the top surface of the silicon chip. So the bottom temperature is T naught, so we can calculate that using this relation, because we now know Ts, we already know the L and Ks values. So this gives us a T naught, which is the bottom temperature of the silicon surface, as 73.8 degree centigrade. Okay, so that's the temperature of the bottom surface. Now the second part for this problem was when for testing we have to run the semiconductor on a high performance, which is high power. So it's given to us that we have to run it for a 90% of the critical heat flux value. So Q naught double prime has changed now. So this Q naught double prime is 90% of the Q double prime max. Okay, so critical heat flux is associated with Q double prime max, that is this one. And remember, there was a correlation to calculate Q double prime max as well, which is this. So we can do that, we can put the numbers, and that gives us a Q naught double prime of 13.9 into 10 to the power of 4 watts per meter square in this case. So again we can use the same ideas as we did earlier, and this results in a surface the bottom surface temperature, or the bottom temperature of the semiconductor, as 82 degree centigrade, which is around 9 degrees more from what we got in the last example, the last case. Now here what's been done is this is actually typically what is done when we are designing as heat transfer analyst. So the temperatures of the top surface, which is T naught, Ts, the top surface is this one, which is T surface, and the bottom surface of the silicon chip, which is T naught, is plotted as a function of your Q naught double prime. So you can see that the temperatures increase with increasing heat flux from the bottom, and the difference between T naught and Ts also increases as we increase our Q naught double prime. Okay, so for a maximum Q naught double prime situation, which is 11.3 watts, 11.3 into 10 to the power 4 watts per meter square, we have in the what's given to us is that well, there's a problem associated here, which said that the maximum temperature that the silicon chip can take without failing is 80 degrees centigrade, okay, which is this one. Okay. So we have to figure out the corresponding heat flux which is the maximum this chip can take. So which for 80 degrees centigrade, since the bottom temperature is higher than the top temperature, so that's the failure criteria, and we get this value, which is 11.3 into 10 to the power 4 watts per meter square, so which is around 73% of the critical heat flux situation. This is critical heat flux. Okay, nowadays, just to comment that the VLSI chip designs we work with, they typically have fluxes which are more than 15 watts per centimeter square. So this is 11.3 watts per centimeter square. Um, Check the units. So this is 11.3 watts per centimeter square, and we are dealing with typically more than 15 watts per centimeter square. So that means that this liquid that we have taken, fluorocarbon, would not be appropriate. So we have to choose another liquid which allows higher value of this Q double prime from the surface. So let us now go through a very quick discussion on condensation. So a couple of general discussions. So heat transfer to a surface in condensation occurs when the surface temperature is less than the saturation temperature of the vapor. And we have two types of condensation. One is film condensation, where a film is deposited, a liquid film is deposited on the surface, and then you have the vapor around it. And as this film provides resistance to the transfer of heat, so the deposition of a film is not desirable, but it is something that happens, and we have to study it. So as I said, that the thermal resistance is is high for this film, but it can be reduced because you have a gravity. So what happens is when the film is formed, the film thickness is high at the bottom because the liquid tends to deposit at the bottom and flows down. So we can reduce this by choosing short vertical surfaces rather than a one long very vertical surface, so that the film cannot go beyond a certain size, and ultimately if it goes too large in size, it results in the liquid dropping off the surface. And this is characteristic when the surfaces are uncontaminated and very clean. So very clean surfaces are not desirable when you want to have a large rate of heat transfer in condensation applications. So the other type of condensation is drop-wise condensation. So as the name suggests, you have these drops depositing rather than one continuous film, and these drops can range in different from size of a few micrometers to agglomerates which are quite bulky. And again, as I said that when drops are formed, it is much better than a film because you still have a lot of area between the drops on which fresh condensation can happen. And these drops, when they become larger than a particular size, because of the ratio of the gravity force to the surface tension force, which is typically called the bond number. When that bond number becomes large, because of the increased size of the drop tends to fall down and the surface cleans itself in the process. So the thermal resistance is greatly reduced due to the absence of a continuous film, and to inhibit the wetting nature of the surface, that is for formation of films, and to encourage the formation of drops. Typically, the surfaces are coated with oil-like substances, and these surfaces then are called self-cleaning surfaces as well. It is desirable that drop-wise condensation happens, for example, on the surface of a windshield in a car, so that you can easily wipe it off or clean it off without the film getting formed on the surface. Okay, so very quickly going through film condensation on a vertical plate. So as we said that we get some sort of a velocity profile because of the presence of gravity, and we also have a temperature profile. I won't go into details of this, but this is for a laminar situation, and we can then solve the momentum and energy equations to calculate the Nusselt number for laminar flow situations on a vertical plate with film forming on it. And when we do that, finally, we can estimate our Nusselt number using this relation, which is obtained from theoretical ideas. Okay, as I said that I won't go into too much detail. So I will quickly browse through these ideas so that you know, have some knowledge of what happens in condensation heat transfer. And when required, you can use these relations or the correlations that we'll discuss soon to solve problems. Okay, so finally, the heat transfer can then be calculated using this Newton's law of cooling, where the average heat transfer coefficient is calculated using this average Nusselt number relation. Area is known to us, and then the excess temperature, which is the difference of the saturation temperature and the surface temperature in this case, can also be calculated with the given data. And just like always, turbulence can also also occurs in these situations. So we have a laminar region in the boundary layer, and then we have something called a wavy laminar region, or a transition kind of a region, and then we have a turbulent region. In this case, the Reynolds number that can be used is based on the film thickness delta, and we can calculate the Reynolds number using these ideas. Again, not going into too much detail, and depending on which region you are in, you'll have to use the corresponding correlation for those situations, if that is the case, or you can also use a common correlation if required. Now, in radial systems, so you also have these pipes, etc., where you will have condensation happening on those surfaces. So one has to study condensation on circular cross sections. So here again, the film looks something like this. So it starts from a um, thin thickness, and then it increases. The thickness increases as you go down because of the fluid, the film tending to deposit at the bottom because of the gravitational force. Okay, and then again you can calculate for a single tube, you can calculate the heat transfer coefficient using this correlation, where the value of C is given as 0.729 for a tube. This correlation can also be used for spheres. Okay. If you have lots of tubes, then the heat transfer coefficient for n different tubes on an average can be calculated like this. So again, without going into too much details, we will move on. It can also happen that the condensation happens inside a surface, that's on the interior of a pipe. In that case, you have a film forming on certain thickness on the inside of the pipe, and then you have the vapor. So you can calculate your you use these relations to calculate the heat transfer coefficient on average. And now let's go to dropwise condensation. So in dropwise condensation, the heat transfer coefficients are really large, and typically they are of the order of 250,000 plus, which can be used when the saturation temperature is more than 100 degrees centigrade. And we are talking about steam condensation on copper surface in this case. Okay, so here's the problem. I won't go into the details. I'll just quickly run you through. So you have a vertical surface on which condensation is happening, and you have to calculate the um, to find the condensation and rate of heat transfer per unit width of the plate, and if the height is halved, then what is the rate of condensation. Remember that we said that typically the size is reduced for the vertical surfaces, because that prevents the film from growing too large at the bottom. So you can use the correlations for turbulent film condensation, because this is a turbulent situation, and that gives you a Reynolds number based on the film thickness as 2979, which can then be used to calculate your rate of heat transfer per unit width of the uh, similarly we have this if you halve things, then you get 300 kilowatts per meter. So which is if you use two of these in parallel rather than having one long vertical plate, that is so having two small plates in parallel is much better than having one large vertical plate. So this brings us to the end of the discussion on boiling and condensation heat transfer as a mode of convection with phase change. And this also brings us to the end of a discussion on the three types of convection. So we started with well, in convection we started with forced convection, then we moved on to natural convection, and finally we have phase change. So phase change phenomena and the corresponding rate of heat transfer associated with that. So this we saw that this is the so if we call this as the H natural, this we call H as forced, and this we call H as phase change. So what we see is typically H with phase change is much greater than H with forced, which is quite greater, which is greater than H for natural convection. So when you have to design cooling systems as heat transfer engineers or analysts, you will have to use these, you have to keep these ideas in mind. Okay, so it was very important we understand these ideas and know about them. But of course, there are advanced books on heat transfer which take you into much more detail when designing systems. The next topic, which will be related to the application of heat transfer, is heat exchangers. So heat exchangers, I'm sure you have seen them. they are you can see heat exchangers in your automobiles, in your industries, and so on, in the heating, ventilation, and air conditioning systems as well, in your evaporators, condensers, and so on. So heat exchangers are very important, and since they apply the ideas of convection, the internal and external both, so we will have a very brief discussion on heat exchangers in the next lecture, where I will tell you about the different kinds of heat exchangers and what sort of calculations or what sort of methods are used for designing heat exchanger systems. But that will be a very brief discussion on heat exchangers, only a couple of minutes, so that if required you can then understand what heat exchangers are, and then you can go into further details, taking help from other design books. Okay, so thank you very much, and I'll see you in the next lecture.